Hello everybody. Let us start our discussion today. So far we have geared up with the ideas why our good old classical mechanics will not work in the quantum regime. We defined what is quantum regime. We also talked about certain mathematical quantities, for example, probabilities, operators, and even we talked about the wave function that represents the matter wave as described by the Broglie. We will accumulate all of these today into the postulates of quantum mechanics. We also talked about the fact that the quantum mechanics or the wave function can be written in, we took two examples, momentum space or position space. But here we will take these things in our back of our mind, that we will write the wave function in position space So psi is a function of x and t. And as you see that we have written only one position x, so unless otherwise stated, we'll consider only one spatial dimension. And as obvious it is, we will call it x. The other thing I will like to remind you that unlike the postulates of special theory of relativity, the postulates of quantum mechanics are not found by a single person. Like for the special theory, it was Einstein. These were developed over a long uh, time frame, about 10 years. Because of that, if you look at different books, you'll certainly find they're not arranged in the same way. So we'll follow one particular style. So if you look at a book and don't find what I call postulate 1 as postulate 1, what I call postulate 2 as postulate 2, uh, don't get bothered. Collectively, all of them should give the same idea. Okay, so remember, one thing we never talked about is what does psi represent, and that from there we'll start our postulates. So let's start with postulate 1. This was giving psi a meaning, giving the matter wave a meaning, and this was done by Max Born. So what is it? It says that the wave function has all the information of a quantum system. Okay, very important. All the information of a quantum system is there in the wave function. So it's essentially in the functional dependence of the wave function. How does psi depends on x and t? Just let me remind you that psi is a complex function. This is just for your remembrance. Okay, phi is a complex function and it has all the information about a quantum system. What is the classical analog to this? Okay, remember that when we were discussing harmonic oscillators last time or last to last time, in the example of classical mechanics, where the harmonic oscillator in the phase space they have trajectories like ellipses, or special case we look at circular trajectories. Now, we also saw, depending on what is the initial condition, I will get a particular energy of the harmonic oscillator, and as the energy is fixed, I will be living in one of those ellipses or circles for that given energy. So the initial condition completely describes the classical system. The initial condition and the potential, if you want the complete information, it's there in that. Here, the wave function has all the information. Once you have find out what is the wave function for a particular system, it has information about the uh, potential also. And you see that it's a function of x and t, so it has to be given at all x and all t. The question is, what information does it carry? The wave function itself, the wave function is a complex number. We cannot measure a complex number in any experiment. So wave function itself does not have any physical significance. What do I mean by that? I do not mean that it does not carry any information which has physical significance. I mean that psi itself does not has any physical significance, which essentially means this implies that psi xt cannot be measured. I cannot measure this. So this is rather a mathematical tool to extract information of a physical system. I cannot do an experiment where I can actually measure what is psi t. It's completely different than your classical counterpart of the position and momentum, initial position and momentum, which we have to measure to get the information about the system. In this case, these cannot be measured. So then, what is that which has physical significance? The wave function can be used to define probability density. Now, see, we are writing a position space wave function, as we said before. Because we are writing a position space wave function, so it can be used to define probability density of finding the particle between x and x plus dx. Remember that we are dealing with only one dimension at the time t. Okay, so how do I define the probability density? So let us call that by pxt. Now we have already talked about it earlier, how we define the probability density, or what do we do with the probability density. Last time we wrote it with a rho. Here it is customary to write with a p. It's not bad because p stands for probability. Now this, remember, psi is a complex function. So I need to have something out of psi which is not complex. And Max Born found out that the best choice is this, and the details of why this is the best choice is again beyond the scope of this course, but take me for granted that it is this. And psi, we have not given any restriction on psi yet, so I also should mention that psi integrated over all space should come up to 1, because that will ensure that our probability density integrated over all space comes out to be 1. Okay, so this gives the probability density. And we have discussed what does it mean. It means that if I consider the region between x and x plus dx in a given time t, what is the probability of finding the particle in that region? So that is given by pxt integration from x to x plus dx that we discussed last time. And this is how I define the probability density. And you see this p is always real, because first of all, that is something that we can measure. We can measure this. Okay, so P is something real. We can measure this, and it is achieved by doing psi star times psi. One thing that I forgot to write here, that we are dealing with one particle only, if otherwise not stated. Okay. All right. Now let's see that what. First, let's ask this question: what psi xt? Psi is a function, right, of x and t. What psi xt? What property psi xt must have? Now, I can just tell you that it will be a function of this type, but I don't want to make it a very mathematical statement, so that's why we will discuss them one by one. First of all, we know, we have already seen that if this is the wave function, at least in one case we know that del psi del x has something to do with the momentum, which means the first derivative of psi must exist, and for a derivative to exist, the function has to be continuous. So psi xt has to be continuous. And I mean at all x. If I integrate mod psi square over the entire x, that should give me 1. Or if I integrate this over entire x, this should give me 1. That we saw is by definition of the probability. Total probability of finding the particle which exists anywhere in the space has to be 1. So now if psi is 0 everywhere, that is not possible, because then the denominator will be 0 and then all here will break loose. So psi cannot be 0 everywhere. It turns out, later we'll see, that not only will require first derivative of psi, we will also require second derivative of psi. So which means that I should say that del psi del x should also be continuous, such that the second derivative can exist. The first derivative has to be continuous for the second derivative to exist. Imagine psi being infinity at a given point, which means that it is possible that the probability if I integrate around that point becomes infinite. So psi cannot be infinite at any point, so this has to be finite at all points. One thing, let me remind you that every function by definition has a single value, unique single value at all x. So I am writing that down, but it's already a requirement for a function. But sometimes we are not so good in mathematics while doing physics, so we write this explicitly, that must have unique values at all x. Otherwise, actually, it cannot be considered as a function. And you see, for all this to work, the denominator must be finite. If the denominator blows up, even if the function is finite at all x, but can be at, say, x tends to infinity, goes to infinity, the denominator blows up, then the probability will not have again much meaning. So which means that first of all, I should be able to do this integral. There are functions for which you'll not be able to do this integral. So I should say that psi, the integral must exist, which the little mathematician's way of writing it is that is square integrable. Okay, so you can think of functions which satisfy some of this criteria and doesn't satisfy others and all, and you can think of functions which satisfies all of these criteria. We'll obviously solve for certain potential cases and we'll see what these are. But this is more or less are the criteria that our wave function should satisfy. Now, before we go further to the next postulate, we realize one thing very hard here, that we are talking about a probability, which means there should be something random happening somewhere. So the quantum system have only probabilistic description. Means that every time I want to measure something, we have not talked about measurement even yet, but it's not that always I expect the same outcome. Now, as we are discussing probability last time, we said examples of coin toss or the shuffling of a dice, rolling a dice or shuffling cards, etc. But all those cases, the probability is of a different type compared to what we have here in the case of quantum mechanics. What is the difference? The difference is the following. In those cases, coin toss, dice throw, or shuffling cards, once you have done the shuffling or throw the dice, you cannot predict the outcome because you did not know all the conditions through which the dice has gone through. Exact amount of force you were given to the dice and the exact initial conditions. exactly how you shuffle the cards, where did you put in which card. But imagine somebody actually know all these, and in case of the card shuffling, there are people who are trained enough to know where does each and every card goes. You may feel that I am bluffing here, but that's not true. There are people called card mechanics who can actually follow the move of all the cards, all the 52 cards as it's being shuffled. They will know exactly, for them, the outcome of the card shuffle is not probabilistic. They'll know exactly where each card is. What I mean to say here is that all these three examples of probabilities, the random outcome is a result of us not knowing something. In quantum mechanics, as we think it is today, the randomness, or the probabilistic description of it, is inherent. It's inherent to the system. It's not just an unknown outcome of what we observe. Okay, there is a very distinct difference between the probabilities in quantum mechanics and in the classical cases. Okay, so all right. So that is our postulate 1, and now we will move to the next postulate, which I call the postulate 2. Now, before I move to the next postulate, okay, let's move to the next postulate. We'll come back to other discussions later. Okay. And this postulate is called sometimes the first quantization. So what does it do? It says with every dynamical variable, there is an operator. With every dynamical variable, there is an operator. Okay. So if we call the variable, say, just for an example, call the variable A, corresponding operator, we write as A hat. Okay. This is the first part of the postulate, and this is called first quantization. And that's all the quantization there is in quantum mechanics. Now, what is the role of this operator? It says if the system, so say the operator is the momentum of this operator is the dynamical variable is the momentum, so the operator is the momentum operator, as we have said. So if the system has a definite value, of the dynamical variable, like for the free particle, the momentum has a definite value. So if the system has a definite value of the dynamical variable, then the wave function of the system will be the corresponding eigenfunction of A, of the operator A. So what will happen now? So A operates on the eigenfunction psi n, or this is the nth eigenfunction. Remember that one operator can have many eigenfunctions. And then what you get out of it is the value, the definite or the eigenvalue and this is the nth eigenvalue times the eigenfunction. Okay. Remember that this we called the eigenvalue equation. Okay. And as we said, that there can be many such eigenfunctions. One operator, an operator can have many eigenfunctions. Okay. Now it turns out, remember that also that our operators are Hermitian, so the eigenvalues are all real. So these are all real. Because see, this is the value. What is happening? The system has a definite value of the dynamical variable. So this is the value of the dynamical variable that we are talking about, which the system, if it already has, then if I operate it with the if it already if it already have that eigenvalue, its eigenfunction, its wave function should be the eigenfunction, and then when I operate that eigenfunction with the operator A, I get that the value that the system have. So this is Hermitian because all the values that I can measure of all the dynamical variables are all real. So this has to be a Hermitian operator. Now there is a property of these eigenvalues. This property is called orthonormality. And this comes from the vector space in which the eigenfunctions reside. And again, I will not discuss it in much detail here because again, it probably will be beyond the scope of this course. But let me just write down and then we will be able to use it later. So this is a property of the eigenvalues. So when I write eigenvalues, I write this suffixes. So it tells you that it's the nth or the mth eigenvalue. Now this is equals to delta mn. I'm sorry, I should not have star in both of them. Is equals to delta mn. Remember that delta mn is 1. So delta mn equals 1 if m equals n and equals 0 otherwise. Okay, so this is called the orthogonality conditions. This we will use later. This expression is just like a dot product of vectors. As you know that for vectors, when you take one eigenvector instead of eigenfunction, there you take eigenvector and multiply it with another eigenvector, then it's always 0. So m not equals to n is 0. If they're the same eigenvector, then the two same eigenvector x cap dot x cap say gives you 1. So that is exactly what it is giving. So it's the same condition of orthonormality of the vectors. So ortho what comes from the fact that if m not equals to n, they are 0, and normality comes from the fact that if m equals to n, they're 1. All right. So this is about postulate 2. And here you see it tells you that if the system have that specific value, and then the system wave function will be same as the eigenfunction and you will always get the specific value. And it looks like at this stage that there is no probabilistic description of this quantum system because it has a specific value. You get out that specific value. Where is the probability? And that comes in the next postulate. So what is the next postulate? The next postulate is about measurement. So this is measurement postulate. So far we said what the system have. We never talked about what will happen if when I measure something out of the system. Now when I say the system, remember that all the information about the system is there in that wave function. Okay, the wave function carries all the information about the system. A general system, remember the previous postulate we said that if the system have a definite eigenvalue, it's given by its eigenfunction, etc. A general system does not have or is not in a definite eigenstate of any operator. Okay, so before we do any measurement, so like let's say before we observe it. Okay, so let's say that we are having we are going to observe the variable dynamical variable a, so the operator is a cap. Okay, so I have this operator. So what so a cap and then psi n are the eigenvalues. So these are the eigenfunctions, sorry. Of a cap. So then a general system, before we do any measurement, I have to write psi xt, which is the wave function, in linear superposition of all possible eigenfunctions. So c1 psi1 xt, all possible eigenfunction of the operator a cap. So that is essentially, I can write in summation n, this is cn Phi-n xt. Some C's are some numbers. So these are some numbers. They can be complex also, but they are some numbers. They are not in. They are independent of x and t essentially. So this is before measurement. Okay. And here comes the most striking difference between classical and quantum system. You remember that classical system, if I tell you what is the potential, and if I tell you the value of the momentum and position at a given time for that particle, you know about where the particle will be at a later time. You also know about where the particle was at an earlier time. So every time where the particle will be or was or is, everything that you know. So that is because all the classical systems are reversible. You can go back to the past. Here, in this case, something remarkable happens. When we measure A, the wave function psi xt collapses to one of its means A caps. If I am measuring A, because we are measuring A eigenfunction. Which eigenfunction it will collapse to is arbitrary It's completely arbitrary. You cannot predict which eigenfunction it will collapse to. So there comes the randomness. Okay. Not only that, if you do any successive measurement, you get the same eigenfunction. So let's see what's happening. So I have this A cap act of measurement. I am operating it on psi. So this psi is x and t. Here the measurement is happening. It's collapsing to the say the nth state. So it is collapsing to this. And remember that A cap is operating on it. So this will give me okay. I do a second measurement. Second measurement, psi has collapsed to this. So psi has changed once and for all. It cannot be changed back to psi and cannot be changed back to psi again. So whenever I do further measurement, I will get back an. Okay, so this is something completely irreversible. This is very, very interesting, and this is something completely irreversible. So as you can see from here, this Cn kind of gives you what is the probability that it will collapse to that state, but we'll come back to that later. But just let me give you a hint. So that is what it is going to give you. So our prediction power seems completely is gone because we do not know which eigenstate it will collapse to. And once it collapses to that eigenstate, so this is just happening by the postulate 2 that it will measure An. Now, sometimes one eigenstate, one eigenfunction, function and state is sometimes used anonymously, used like same because the state of a system is given by the wave function, as we said in the first postulate. Sometimes one eigenfunction is shared by two or more than two operators. Okay, sometimes there is one eigenfunction psi n, say. This basically means that if I do this, it gives me an and then psi n back. Remember that if this is the eigenfunction of that operator, that is what has to happen. That it should spit out a number and then give back the function again. If it doesn't do it, then it's not an eigenfunction. But it is also an eigenfunction of the operator b. In some cases, so maybe it's the mth eigenfunction of the operator b as the same function. So let me not distinguish. So let me not distinguish here because it's the same function, exact same function, eigenfunction of two different operators. It can so happen. So then what happens is, in this particular case, if I measure A first, so I do the measurement. So measurement is essentially in quantum mechanics operating by a wave, operating by an operator, the measurement operator, which corresponds to what you are measuring, the dynamical value you are measuring, and you operate that on the wave function, the state function. So if I measure A cap first, then psi xt will collapse to, collapse means that it will lose its identity, its earlier identity. It will assume one of the eigenfunction of A. Collapse to this. First this will happen. Then A cap will act on psi n, will give you A n psi n. And if I measure, then if I measure B, then what will happen? Then you see that is B cap on psi n again. This will give me B and psi n because B, it's also a wave function of the operator B. So which means that if I do this, I can write this together. This just will give me okay, and this will happen only if the eigenfunction is shared by the two operators. So the same eigenfunction is the eigenfunction of the two operators. If it is not so, then what will happen? So let's say we have an operator C. Okay, another dynamical variable which is another operator C. Now C A cap and C does not have same eigenfunctions. So what will you do? So we'll first do measurement by A. So then what will happen? So measurement by A is, so it start with, it is in some arbitrary state psi, it will collapse to one of the eigenstate of A. So let me write that as A here, with A here. Okay, let me write it properly. So it's A. So it's an eigenstate of A. And it's a nth eigenstate of A. So say it's the first eigenstate of A into which it has collapsed, A1. So this is collapse. And then you will do this, obviously. This will give you A1. Okay. So see, the wave function has given you the number, but the wave function is still there. If I want, so now I say now I want to measure. Now I want to measure the other dynamical variable of which the operator is C. So C is the dynamical variable. Now you see psi A1, as our assumption is not a eigenfunction of C, but I can write this in terms of the eigenfunction of C. So this is an arbitrary state as far as C is concerned. So I have to write this as an eigenfunction of C. So this will be now first written this way. And again, when I do the measurement, then psi A1 will collapse to one of this Cn, and then you will make a measurement with C, and you will get Cn psi Cn. Okay. So you see, it's a completely different process when A and C does not share the same eigenfunction. And you can imagine, now if I use A first and then I use C, I will get one outcome. On the other hand, if I use C first and then I use A, I will get another outcome. Which means essentially, let me write this statement and let me ask you to think about it. If for two operators A and B, their commutator, as we discussed last time, which essentially when it operates on a wave function psi, it means first you try with B first and then A, and then you try with A first and then B, and see what is the difference between these two. If for two operators A and B, this equals to 0, then as we saw, they will share same eigenfunction. Okay, so this is about the postulate 3, which so postulate 2 told us that it is kind of going to be non-probabilistic, and postulate 3 now tells us that it will arbitrarily collapse into whatever state it wants, and it is absolutely probabilistic. You don't have any way of predicting which state it will collapse to. So then what is the point? So if we cannot predict anything, then you don't do science, right? Science is there to predict the outcome of the experiments. So where is the prediction? So that will come in the next postulate. And here we discussed last time the idea of expectation values. It is these expectation values that one can actually predict. We can predict the expectation value of a measurement. How do we have to do the expectation value calculation? Well, what we have to do is, see, if I measure only one case, then obviously it will scatter, it will collapse to whatever it wants. But what if I create many, say 100 different wave functions which are exactly the same? The state of the system is same, which means the wave functions are same. And I operate on them with my favorite operator, say a cap, 100 times, each of them separately. If I do that, then I can tell you what is the average outcome of this experiment. Okay, so what is the average value if a cap is the momentum operator? I can tell you what is the average value of the momentum operator, and that is defined this way. So remember, we defined the expectation value last time, like rho. If it is the expectation value of a, it will be a times a as a function of x times rho x dx, where rho is the probability density. In this case, it's an operator, so it has to be sandwiched between the two phi we had. So it is to be like this. So that is the definition of my expectation value. Now you give me an operator and you give me the wave function on which I will be operating on. I can tell you, if I do 100 times the experiment, what is the average of the expectation value of that experiment. So this is something which I can predict. So what we have learned so far? We have learned so far that quantum mechanics is a complete probabilistic theory. All the information of this theory is there in that wave function. All the information about the system is there in that wave function. The wave function, to start with, is in a general wave function. It doesn't care what operator you want to use. Obviously, it will not know which operator you are planning to operate it on. But once you operate on with your favorite operator, it will collapse to one of its eigenstate, and once it collapses to that eigenstate, that is completely irreversible. It stays there. Every time you measure with your favorite operator after that, at least immediate after that, you will get the same eigenstate. And that's a complete random process, so I cannot get a definite outcome out of it. But what we can say is, well, if I do this experiment now 100 times with the same type of wave function, with the same operator, then I can predict what is the expectation value, what is the average outcome of those 100 experiments. So just a vague example, if I am coin tossing, so I can predict what is the average number of times it will turn out to be head. And that is by this way. So it's almost like the way we calculated expectation values earlier. Remember, chi star chi gives you rho in this particular case, but here a has to be sandwiched between two chi's. Otherwise, see, it's an operator. In the right hand side of it, there has to be a function. Otherwise, it doesn't have much meaning. Okay, so that is postulate 4. And let's quickly go to postulate 5 and we'll carry our discussion from there. So what is left for us What is left for us to know is how to know psi. How to know psi. Well, one equation, if you remember, we already had wrote down for psi just when we started our discussion on waves. We said that for at least for the plane wave, where I have free particle, if you look at your notes, you will see that this was the equation which psi will satisfy, given that your energy and momentum is related as E equals to p square by 2m. So it is a free particle, no potential. Okay. If I investigate it a little more now I know that IH cross del T, this was our momentum operator, energy operator. And remember, our momentum operator was minus IH cross del X. Okay, so this is what we discussed in the last class. So these were our energy and momentum operators. Okay, if I look at this equation, you see what it is just IH cross del T times psi, and in the right hand side, if I have minus IH cross del X whole square, that will give me h cross square by 2m del 2. This is not, sorry, there's a mistake here. This is del x2, not t2 on psi. So this essentially is E in the left hand side, and in the right hand side what I have is P, this I need a 2m also, divided by 2m. Okay, remarkable, because if you look at now the energy and momentum relation, it looks almost like that. So it was suggested by Schrodinger that if we have an electron, a particle, rather, let's not say electron, a particle in potential V as a function of x and t. So how is the energy momentum related then? So you know that energy is, as it's given by the Hamiltonian is p square by 2m plus v x and t. So this energy will can be a function of time, because this is a function of time here. So this part we called kind of Hamiltonian, and this we call the energy. Now both these quantities p and v etc., they are all dynamical variables. So in quantum mechanics, I should change my E to the energy operator, which we did earlier. So this should be replaced by IH cross del T, and this should be replaced by p square by 2m, which we have already seen is h cross square by 2m del 2 del x2, and this remains vxt, and these are operators, so they should operate on psi. This entire thing should operate on psi. That gives me now an equation for psi. It's a partial differential equation for psi. It's almost similar like this. Only thing we have added is the potential term here. It's exactly same as this, just the potential term is added. So let me write it down more properly here. And this is what will, if I solve this for a given potential and boundary condition, then I will get what is my, I'm sorry, so there's no minus here, just plus. Then I will get what is my wave function. And once I know what is my wave function, then as we said, that has information about the entire system. So I will know about the entire system. So this is called Schrodinger equation. And that ends our discussion on the postulates of quantum mechanics. We'll start using it from the next class.